When we push contemporary large language models past a specific context threshold, we hit a hard thermodynamic and epistemic asymptote. Autoregressive architectures are highly optimized for next token prediction. As long as a prompt remains within the statistical boundaries of the model's pre-training distribution, the output is coherent. But introduce highly complex, out-of-distribution constraints at the 1 million token horizon, and the architecture breaks. Documented as the illusion of reasoning, the model abandons its rigid constraints and regresses to statistical averages, a phenomenon characterized by entropic wash and semantic saponification. This happens because standard models treat semantic meaning and causal logic as emergent byproducts of syntax generation. They calculate that if the grammatical structure is highly probable, the logic must be correct. To scale toward environments that demand autonomous, human-independent scientific discovery, we have to abandon linear sequence prediction entirely. Systems that guess the next semantic token are mathematically incapable of retaining complex invariants across extreme contexts. We require a computational substrate built on physical topology rather than probability. Surviving these extreme context horizons requires an alternative structural approach, the Sovereign Cognitive Operating System, or SCOS. First, the SCOS abandons hard-coded exogenic assembly. Instead, it utilizes endogenic autopoiesis, meaning the system leverages its own internal metacognitive frameworks to write and execute its developmental lifecycle. To prevent the gradual goal drift that corrupts long-horizon autonomous tasks, the architecture establishes teleological anchors within its first dimension of control. These anchors operate as vector-based alignment thresholds, measuring cosine similarity against invariant North Star objectives to reel in aberrant processes. The second dimension introduces anionic anti-goals, a negative space topology that physically blocks unauthorized network calls or destructive commands, enforcing a firewall directly at the logit level. By replacing probabilistic guardrails with rigid mathematical decorators, the latent space transforms from a fluid guessing engine into a strictly bounded geometry. Analyzing the failure of extreme contexts requires us to apply Hickham's dictum, which favors multi-causality over the simplicity of Occam's razor. The current industry assumption is that KV cache memory explosion can be solved by simply evicting tokens with the lowest attention magnitudes. This is a severe oversimplification. We have to evaluate text through the Region Connection Calculus, or RCC8, spatial lens. Under this framework, text is not a linear string of characters, but a series of overlapping regions of meaning. The preposition inside, for example, acts as a non-tangential proper part operator, connecting distinct semantic volumes. If an eviction algorithm drops that operator to save memory, it collapses the topological boundary, merging the interior and exterior contexts, destroying the logical structure. To counter this, the SCOS implements a spatial bind decorator, invoking the RCC8 calculus to force the model to prioritize boundary verification over mere semantic saliency. By explicitly tracking these spatial volumes and their boundaries across millions of tokens, the architecture drastically reduces topological contradiction errors. Within this framework, syntactic operators serve as the physical, load-bearing walls of the cognitive manifold. Calculating these spatial boundaries requires mathematical precision that discrete, easily corrupted vertices cannot provide. This figure from the Geo-to-Vec research demonstrates how geospatial entities are mapped as continuous signed distance fields, or SDFs. The math relies on an SDF gradient. Negative values map to the exact interior of an entity's boundary, while positive values map to the exterior. This continuous, differentiable representation bypasses the limitations of vertex-edge models, allowing the system to perfectly capture spatial extent and complex topology without fragmentation. The SCOS extracts this exact geographic math and applies it directly to abstract semantic spaces, laying the foundation for the anionic architecture.
Illogical or unsafe parameters are mathematically forced into the negative value zones of the semantic SDF, trapping dangerous vectors in conceptual voids before they execute. Adapting continuous fields to semantic logic creates a unified representation where boundaries are explicitly defined. This rigorous mapping introduces a critical tension. What happens when two spatial concepts violently contradict within a strictly bounded topology? We can model this using the DE9IM matrix intersection. Specifically, the string 212101212 characterizes a state where two solid interiors attempt to occupy the exact same spatial coordinates. In a pure Euclidean simulation, this is merely a static anomaly. But within physical engineering and the SCOS framework, this intersection dictates an absolute kinetic mandate. One structure must yield, deform, or shatter. Standard transformer architectures fail here. Unable to resolve the spatial strain, they wash out the contradiction into a generic output. S5 modal attention solves this by engineering para-consistent non-separable conjunctions, allowing the system to hold mutually exclusive constraints simultaneously. It maintains these high-tension, non-separable states without catastrophic forgetting by utilizing holographic reduced representations and continuous circular convolution. Sustaining this para-consistent logic is what empowers the architecture to execute structure mapping theory. Structure mapping theory bypasses standard Euclidean dot product similarity, which relies on superficial overlapping attributes. Instead, it allows the system to map deep relational structures, aligning non-Western pluriversal ontologies, such as linking the biological mechanics of mycology directly to Andean indigenous governance models. By treating contradiction as a structural opportunity rather than a statistical error, the system bypasses heuristic colonization, achieving actual analogical reasoning. Spatial calculus and para-consistent attention merge into the final overarching framework, the autopoietic neuromorphic pluriverse, or ANP. The ANP realizes true endogenetic autopoiesis by using specific grammatical function tokens to dictate spatial routing across its middle compute layers. Consider basic syntax routing. A new line acts as an orthogonal shift, completely flushing the semantic buffer, while the preposition of triggers hierarchical mereological binding. The mereology root decorator enforces Winston's part-whole models. This mathematical boundary verifies the hierarchy, preventing localized variables from corrupting global types. This explicit spatial routing completely mitigates the lost-in-the-middle anomaly, allowing flawless accuracy and retrieval even when querying 1.5 million token-federated documents. In the ANP architecture, grammatical classes act as rheological valves that physically direct the flow of cognitive attention. A critical question remains: how do we prove these high-dimensional spatial hypotheses are actually tethered to physical reality, rather than just hallucinating formatting compliance? The system grounds itself through an empirical actuation layer. Latent hypotheses are instantly translated into executable operator contracts. These contracts deploy the Helix, Maxima, and Sphinx robotic swarms via the AIMD laboratory, subjecting predictions to extreme physical friction using lasers, X-rays, and nano-indentation. The resulting real-time empirical data streams directly back into the latent space through the causal grounding engine, relying on encoder-decoder cross-attention. The epistemic escrow decorator evaluates the physical data. By forcing the system to halt immediately upon physical divergence, it eliminates the causal efficacy paradox. The cycle is complete. Text calculates as spatial geometry, para-consistent logic holds the contradictory tension, and robotic swarms provide empirical verification. Scalable, autonomous intelligence now requires the continuous, verifiable calculation of structural truth, moving past the limitations of purely probabilistic prediction.